First order reactions. In this video, we're going to do basically everything that we did in the last video for zero order reactions again, only this time looking at it for first order. So we again want to identify the graphs of concentration versus time. And this time it's going to change a little bit too, because now we actually need to also understand how we can get a linear graph from that data. As scientists, there's a lot of times that it's very useful for us to have linear graphs. We will give you the integrated rate law again. I'm not going to explain how we get it this time. We talked about that last time. So in this case, you'll just be given it. And then the half-life formula. Just like with zero order, you should be able to go in between your initial concentration, final concentration, time, half-life for any given set of information. And we'll do some examples in this one too. We kind of skipped that for zero order since those are the easier examples. So for first order, we have a very different looking rate law. And that's because we know that our first order rate law is equal to rate equals K times the concentration of A. The last one, we didn't have the concentration of A in the rate law. And so our integrated rate law was much simpler. For those of you who are comfortable with calculus, you may want to look at this and you can kind of see where it comes from. It's a little more advanced than just calc. It's actually diff EQ. And so you might not be able to actually do it, but you can see where this natural log comes in based on the integral of K times A. Now, when we graph this means that our graph is actually an exponential decay. If we look at as time goes on, our concentration is going to decrease, which decreases our rate. And so you don't just get a straight line anymore. You get what looks like the bottom line on this graph for the most part. Now, something I wanted to point out is that your size of K is going to change what this graph looks like. And so you could actually end up with something that looks very much like a straight line depending on the size of your K. And so you should mostly be aware of that in a lab context where you aren't told if something is a zero first or second order. You have to decide. You may want to actually always check your graphs and see if they're more linear or if they fit better to a natural log than they do to a linear. And that'll make more sense once you do this in the lab. Now, the linear graphs of pretty much anything are easier for us to work with. And so for kinetics, we like to be able to change these into linear graphs. Now, there's no way that we can magically just make this a linear system, but what we can do is change how our axes on our graphs work. So if we look at this and we look at our rate is equal to K concentration of A, and we think about what that means in terms of our integrated rate law, what we can do is instead of just making the graph as related to the concentration of A on our y-axis, we can actually change the y-axis into the natural log of the concentration of A. So if you look at the second graph on this, you can look at the y-axis and you can see that it's not just the concentration of A anymore. It's the natural log of A. Our x-axis, our horizontal axis, is still time. This gives us a straight line with a slope of negative K. You can also at this point basically see the integrated rate law in this because our y-axis, or our y-intercept, is going to be our natural log of our concentration of A. So we can use these for a variety of things. Let's first do a quick summary of everything we've just talked about, and then we'll do some problems. So we have our rate is equal to K times the concentration of A. We have our integrated rate law, which is our natural log of AT, or our concentration at time t, over top of our concentration, our initial concentration. And that's equal to negative KT. So if we just graph this, we get a natural logarithm graph, which is not particularly easy to deal with. And so instead, we will often see it as graphed as the natural log versus t. And if you're doing this in the lab and you don't know what kind of reaction you're dealing with, this is a really easy way to check that, because you could graph t times concentration and see if it's linear. And if that doesn't work, you could graph t times the natural log of A and see if that's linear. And if that doesn't work, well, you have to watch the next video to find out. Now, I'm not going to do the derivation for the half-life here. I'm just going to give you the formula. So the half-life formula for this is T1/2 equals 0.693 over K. Now, something that you need to do on your own is derive that and make sure that you can do that. It's the exact same protocol that we did last time, using the fact that AT is equal to 1/2 A naught and filling it into the integrated rate law. So take some time and do that and practice working through that, and come ask for help if you need it. Now let's do a couple examples using this. So we didn't do any examples for zero order because those are a little bit easier mathematically to handle. So I wanted to save all of our examples for this one. So here I have that beta blockers are a drug that are used to manage hypertension. It's important for doctors to know how much of it is used up over a particular amount of time. Typically in the medical field, we talk about everything in terms of half-life. So I tell you some data here. I tell you that it's eliminated in a first order process. So by telling you that, I'm telling you which equations you can use. I'm telling you that you want to use this integrated rate law. So by looking at this now, we can look and say, okay, do we have an initial concentration? And we do. And then I can also, well, we sort of do anyways. I didn't actually give you an initial concentration. What did I actually give you? I gave you mass. And we can look at this formula and we can say, but this is concentration, not mass. But here's why it works, and here's why we can fill it in, and here's why I picked this example, is to show you this, is that AT and A0, or A naught, are going to be in the exact same solution. So, if we, and they're the same material, so they have the same molecular mass and they have the same volume. So by doing this, we would be multiplying the top and the bottom by the exact same number. And we can go ahead and we can decide then that it's okay to fill in mass. It's okay to fill in milligrams even. And we don't even have to convert it to grams or kilograms, because no matter what we multiply the top number by, we're going to be multiplying the bottom number by the same. From here, we can fill in K directly. I give that to you. And we can fill in our time. Now, when we're looking at our time and our K, the most important thing here is to just make sure that the units match. And they do. I gave you the time in minutes. Well, I gave you K in minutes. So I had to fill in time in terms of minutes as well. So let's look at all of this now completely filled in. K is filled in identically. I changed my T into minutes. 5 hours times 60 minutes is 300 minutes. I filled in my milligrams directly, and this will allow me to solve for my natural log of AT. So when I do this, I can now solve for my natural log of AT. I can now take this and keep in mind that whatever units I filled in for my concentration, in this case milligrams, because I was able to do mass, that's what I'm going to get back out. And so when I do that, I get 1.0 milligrams. Now there's some things you should double check here. We're looking for a final concentration of a reactant. It should be smaller than what we started with. If it isn't, something went wrong somewhere along the way. You messed up an exponent, or you messed up a negative sign, or you messed up filling it into the proper variable. So we want to check that. And it is a lot less, and so we're probably okay there. It's a good check to do. Now let's do another example. It's very similar. So in this case, we have ethane. And I say that it forms CH3 radicals at 700 degrees Celsius. And I tell you that it's a first order reaction. So again, I'm letting you know when I tell you that which equation set you're going to need to use. That you're going to need to use the half-life in the integrated rate law that we talked about in this formula, or in this video. I told you what K is, so we have that. And now I ask you, first, this is actually going to be a two-part question. So for here, I ask you, what is the half-life for the reaction? And then for B, I say find the time needed for a certain amount of ethane to fall to another amount. So when I tell you that I want you to find the half-life, you have to know to go get the half-life equation. And it's a first order reaction. And so you're going to use the 0.693 over K. Now, very simply, you fill in K and you get your half-life. So nothing particularly complicated there, just filling into an equation to get a number. So now for the second part of this, we need to think about what equation we want to use. We know it's going to be one of the first order ones. And we have a reaction that is going from one concentration to another. So that should signal in your mind that we're looking for an integrated rate law, because that's what we use when we have concentrations changing. So we pull our first order rate law, And now we have to very carefully look at our concentrations of everything and decide what to fill in. So I tell you how many moles it's going from and to. Now, just like last time when I gave you milligrams, you might be saying, but wait, this is a concentration. Don't I have to fill in a concentration? And that's true, but for whatever reaction volume it is, it's going to be the same for both AT and A naught. And since we have a fraction here, then it's going to be the same number that we divide by in each case. So they cancel out. So the practical upshot of that is, yes, you can just fill in moles and it's okay. So we do that. We fill in our moles on each one, being careful to make sure that we put our final on top and our initial on the bottom. We fill in our K. In this case, we're solving for T, so it doesn't really matter what our concentration for K is. So I left it alone in hours. And what that means is whatever time that comes out of this is going to be in hours as well. So I type this in, I get my answer, and I have the amount in hours. And if I wanted that in minutes, I would, of course, just multiply by 60. So now let's do a quick summary review of everything that we did for first order. We knew our rate law from before. We knew that our rate is equal to K times the concentration of A. We gave you the integrated rate law for this, and actually I just gave you the half-life too, although you're going to solve for the half-life on your own time, like we did in the first video. So now you have your integrated rate law and your half-life, and you can use this to go back and forth between any of the variables involved. We know what our graph looks like. We know that it's a natural log graph if we have T versus concentration. And we also know that we can get a linear graph from that by doing T versus the natural logarithm. Now, if we do that, if we make it a linear graph, T versus the natural logarithm of the concentration, we can also find the slope of the graph and use that to find K. Now, for all of these, we can have various different types of questions, and you shouldn't take just the two that I gave you here to mean that those are the only questions you could be asked. You want to look at all of your example questions to find out what any concentration is at a given time, or what our K is, or what our half-life is.